Today is going to be, the first part is going to be, similar in the spirit of what we did. And then we are going to switch gears, and I will start talking about the motion of fish. And what I wanted to start saying, by the way, is that maybe, because you don't have, maybe some of you, a lot of experience, you feel that these fields of synchronization, collective motion, the brain, opinion dynamics, are fields that are very separated. Yesterday I had the opportunity to interact with some of you, and you were saying, oh, but that's not my field, really. Well, I believe that the border in between these disciplines is very diffuse. So I'm going to show you in today and tomorrow's maybe presentation that the talk of Ulrike continues being helpful for understanding the behavior of animals. And this synchronization phenomena that we have been discussing through the use of oscillator, phase oscillators. I don't know about all of the types that you can find in the literature, but this also could be at least helpful in order to understand some of the problems that the nearby community working on collective motion and collective behavior actually is doing. So yeah, keep this open mind and perspective. Don't try to parcel stuff, because it's not good. And you will see opportunities in the future just by making these connections in between the fields. It's my recommendation. So with that spirit, I start this second part today about the bees problem. I just put the slide that we were using yesterday for the kilovolts to try to remind you what we were worrying about. So the idea is that they have to decide where they go together to one side or two sides. I mean, yesterday we were discussing it in general, in which the sites actually could be different from the point of view of quality. But this is a general setup. And today, in a moment, after I discuss something that I left out yesterday, you are going to face a situation that I advertised yesterday that is more dramatic when you have to choose in between options that are very similar. No, they don't have to be mathematically identical. If they are very similar, I think that in nature you will face exactly the same problem, although mathematically you won't have a singularity as you do here. Okay? But let's go. Okay, so remember, now the students did the hands-on session yesterday. Some of them even started to simulate this phenomena. And so you know much better now what's going on in here. So the idea that I told you, I promised you that I wanted to convey is that it is true that I care very much about bees. So everybody is caring about bees nowadays. But it is true that what we do here is a little bit more, ambitious, because eventually we had this idea of extrapolate, let's say put these ideas in synthetic swarms that are able, for instance, I don't have this figure here, but this beautiful paper by Andrea Giovanni Reina, in which they formulate the problem. Imagine that you have these swarms, these boats that are flying in the air, and they have to decide whether they want to go, and there's a fire in the forest, and you have to decide where to go first, to which front of the forest fire you have to go first. So they will have along the way to the forest to decide what is the most dangerous place that they will have to start, maybe putting some water or something like that. And here you see the movie that some Chinese people put on the YouTube or on the web. They have these drones and they are exploring this forest. It's the first time that they see this forest, and they find a target. They have to find a target through the navigation, and actually they communicate like our kilobots in very simple terms in order to track the space and find the target. And this is something that it's advancing so fast that I believe that we are going to encounter it maybe in our lifetimes. I don't know. Maybe we are going to see these applications. Apart from the military, this is what you have over there. There's the military are advancing very fast in these things, because even the drones want to decide whether to put the bomb here, there. That's more dangerous. But hopefully they are not cheap as the kilovolts, and they are a little bit more expensive and know much better what's going on. Anyway, it's just a motivation. So yesterday I told you about the similarities of this superorganism idea, a brain that it is made out of units that are the bees or the fish. And I wanted to comment to you that this superorganism has some properties, such as the one that I have in this slide, which is something that it is nice. Maybe you have heard about the Weber's law. It's a psychological law, so it's something that the psychologists will know. But we all know from our daily experiences. If there is a lot of noise in this room, if you want to distinguish my conversation with somebody, with a colleague here, if the noise is very big, I will have to really talk much louder in order for you to understand what I'm saying, right? So this is actually what it is known as the Weber's law. The idea is that you are able to resolve differences, this will be the speech, that are proportional, that behave in a linear proportional manner with respect to the base stimulus. So if there is a lot of noise and the base stimulus, the noise on average, is giving you a lot of frequency here, then you will have to be able, you will only be able to resolve differences in the conversations if we speak very loud. Otherwise, you won't be able to distinguish our conversation because it's melted with the noise. This is the Weber's law, and they use it for different stimuli. And in particular here, we are applying this to the possibility of these bees to resolve differences in between quality of the sites, which depend on the average quality of the sites, because this is a parameter that it is free, the quality. So the quality big, actually, here will represent that the difference that you are able to resolve in between qualities is proportional to this average quality that you have in your system. And we actually corroborate that in this model, this is fulfilled. What does it mean? That bees will be able to distinguish in between two different sites, but the difference in between the qualities of these two sites have to grow linearly with the average value of the quality. Okay, this is something that it is fulfilled in here. This model verifies this law, which is known in other contexts. It is the Weber's law. On the other hand, it's nice from the point of view of the model. Why? Because what matters is not exactly what is the value of the cues that you use in the model. What matters, and this is what we corroborate in this graph, is the difference in between them relative to the average value. So you can play around with different values of Q normalized by the average value of these two possible sites, and you will see that it does not depend, our results about the strong consensus, no consensus, and so on and so forth, will only depend on this parameter that is comparing the qualities relative to the average value of the qualities, which is nice, So it's not parameter dependent. It's something that it is nice. And this is what I am showing to you here in this slide, and this is the message. Actually, you can represent it in different ways, but essentially this is what I am saying. The difference that I am able to resolve, that the bees are able to resolve, what does it mean to resolve? That they are able to reach the strong consensus, in that case, will be proportional to the average level of these qualities that you have over there. Okay, and there is also a finite size effect. So the more agents you have in your system, actually, the smaller the differences that you will be able to resolve just by this size effect, which is also something that it is very nice. So more is better in this case as well. If you want more details, I sent to Umberto and some guy there in the office, that slide with the suggested reading. It includes 3 of our references that I am also putting in the slides. But for some reason, I didn't see them this morning, so I sent them back again, the slide with the references. Hopefully now they will hang it there together with the videos. There are the videos also of the presentations in the web page. Okay, so let's come back now to the normal problem, and let's focus, as I was saying, in this, what we call a difficult problem of choosing, deciding, and getting enough consensus in between options that are now very similar. In particular here, mathematically, I'm representing that these qualities are going to be exactly the same. So 2 sites out there, and I have to get the quorum for the whole system to go to one of them, and now I don't have no inequality difference that can help me in doing that. So now mathematically, just with what you did yesterday together with me here, no, we had these equations for the fractions of b's that we are dancing for any of the choices. Now you can, this is the homework that I also wanted you to do, you can write down the equation for what we call the total number, the total density of active bees. This is what I'm going to call rho, is the density of bees that are committed there. And if you write that equation and use this scale parameter lambda, which is actually taking into account both, remember lambda was the imitation parameter. No? If it's close to 1, I rely very much on imitation. If it's close to 0, it's just the independent discovery. And then there was another parameter, R, remember, in the equations, and that parameter was controlling, due to the quality of the sites, the abandonment rate of the site for which the bees were voting. So now lambda is a rescale parameter that contains the two, the lambda and the R. And if you do that, this is the equation. And maybe for some of you, if you have a little bit of experience with this reaction diffusion and the contact process and so on and so forth, this is a deterministic contact process. So it's the model, the paradigm model, let's say, for the spreading of diseases. So this is the equation that you get also in this particular case, but I have to have these requirements that the qualities are the same and that I have set this parameter pi so far equal to 0. Okay? With the pi, it's okay. I mean, it will be like a field that you use in order to perturb the system. But so far, let me just put it equal to 0. So that's the equation. And if you are familiar with that, actually you will find easily the fixed points are 0 or different from 0. And actually there is a phase transition that it is continuous. It's a critical point, that it is separating these two stable solutions depending on the value of this parameter lambda that it is controlling the rate of imitation with respect to the rate of abandonment. So this is exactly mappable to this problem that it is called the contact process. That is one way of, for instance, understanding the epidemics, whether you have some people that are infected or you don't have any people that it is infected with the parameters that you have in those models. It's exactly the same problem. Here I'm showing you the deterministic solution, and this is the result that you are expected to find if, as I told you, you do the simulations in this case, after averaging over several realizations and taking the mean of the steady state for the different values of this parameter that we were using yesterday in the hands-on session. Very good. So we have a critical point, another signature that actually makes this system of bees deciding for the next home, very similar to what, apparently is happening in our brain. You probably all have heard about the criticality in the brain hypothesis, the brain critical hypothesis. So here we can also have a critical phase transition that it is separating. But it is not just rho that I care about. Why? Because rho is just the sum of all those individuals that are either voting for option A or for option B. What I need to also introduce in here is the parameter that breaks or could break the symmetry in between the two options that now are equivalent. And I will call that consensus if you want, or even magnetization if you want, because it's just going to compare the number of spins going up, the number of bees voting for one option, and contrasting that with the number of bees that are voting for the other option. This is what I call M. But before that, let me remind you, remember, these are the two qualities here are not the same, because if you deterministically put exactly the same qualities, if you did the homework, or maybe you can continue later this evening, you will see that deterministically speaking, you will end up in a deadlock. Well, it depends on the initial preparation of your system, actually. But if you prepare your system, for instance, with equal probability of finding the bees in the three possible states and committed, voting for A and voting for B, deterministically speaking, this deterministic equation is actually not going to allow you to form consensus. You will stay in an uncommitted state, and the fractions of bees dancing for the two options are going to be exactly the same. So no consensus, because consensus means that, more go to one of the options than from to the other, okay? So I told you that the consensus here now is not for exactly the same, but you can imagine, you see that close to the pi going to 0, which is what you see along this red marker that I have put over there, the consensus is very high, and actually for a broad range of the parameter values that you see over there, for the parameter lambda. So that's a nice region, actually. Why? Because when you make this pi equal to 0, the consensus actually is more widespread along this direction of the phase diagram. Second of all, as I was telling you, if you introduce this idea of controlling whether the symmetry has been broken or not, you will see immediately in these simulations, stochastic simulations, I mean, it cannot be found only with the mean field equations, that the symmetry is spontaneously and always broken. So once the system actually passes through the phase transition that I have shown you in the previous page, so when we have particles dancing for any of the options, fluctuations, finite size fluctuations that come naturally in this system just because of the finite size are going to break for you the symmetry spontaneously. So as opposed to what you see in the deterministic treatment, here the fluctuations immediately are going to go in one direction that actually will fix the population completely, whatever the population is there that it is voting, in one of the options. So it's not that consensus is possible, it's that you get unanimity, and this is just an effect that it is introduced by finite size fluctuations, which is very nice. So what else can you do from the master equation that we were actually studying together yesterday? Well, these are the exercises that I was proposing to the students. Doing this Gillespie or agent-based that I told you how to do. Maybe some of you had advanced. So the idea is that if you do that, you will see this phenomenology that I was commenting and continue with the master equation. Actually, you can introduce the first corrections that are due to this noise, that it is intrinsic in the system just because it is finite. So with that, you can actually arrive to what we call a Langevin type of coarse-grained mesoscopy equation with the deterministic part, which is exactly the same that we had, but now with a noise that it is correcting those results. And the noise that you will find, and if you are interested, I can explain you how to do that at the lowest order, is going to be what we call a multiplicative noise. So maybe you are familiar, maybe you are not. So the idea here, you see, this is not the coefficients that will characterize the intensity of this noise that is of the Wiener type. So no correlations in time for this stochastic noise that is the result of the analytical procedure at the lowest order. It's going to be multiplicative, as you can see in these coefficients that are the ones that are non-zero here. They are proportional, sorry for the change of notation, I just copy and paste. X1 and X2 here are exactly the same as the F1 and F2 that we were working about yesterday. Sorry for that. And you see that inside the intensity of this diffusive type of behavior that you will have represented by these Wiener processes, you have the fraction of B's either in this term dancing for side 1 or the fraction of B's dancing for side 2. So if fluctuations allow you to, for some time, just because you start doing that, reach the place in which one of these fractions is 0, just because of the fluctuations and the finite size of the system, then you will stay there forever because the noise is not going to take you out of there, because the noise there is going to be 0. So it's an absorbing state, in which not even the noise actually is going to be able to take you out of there. So this is the form of this Langevin equation in what we call the Ito scheme. And if you write it in what we call the Stratonovich, there are technical things. If you are interested in that, I can also talk to you later on, but just for those that are interested. You see that there is a tendency for this, what we call magnetization, which I will, it will come maybe in the next slide. It was also in the homeworks, remember? Here I was telling you, write down the equation for both, the total number of agents that were dancing for any of the options, rho, and also the difference in between the two, this consensus or magnetization, if you want to understand it this way. So for this M, actually, when you write this Langevin equation, you see that there is a drift that takes, no, the fluctuations are taking this M out of 0. Naturally, spontaneously, always. There is no exception. So always in those simulations that you are doing, if you have a finite number of agents, even if it's big number, it will take maybe more time, but eventually the fluctuations are going to actually break the symmetry in between the two options, and you are going to have unanimity, which is very nice. This is something that can happen in this model that is addressing, no, a problem that it is important for the decision in nature. No? I find it nice. I didn't expect that. Okay, but then you will ask the question, yeah, but for that to work, pi has to be 0 or very close to 0, because if it's still very close to 0, you will feel the effects of the critical point nearby, and you will have scaling exponents, no, as in normal phase transitions. But how, I mean, the system is choosing the value of that parameter, and how actually, you know, is in a autonomous manner going to go, to put this parameter pi very close to 0. How do you do that? Well, you can think natural selection. No, well, there are ways in which these bees actually can tune the parameters so that the system is in the neighborhood of this critical point, or in this region in which the fluctuations will break the symmetry of the options for you. Okay? How do we do that? That's another interesting phenomena that I wanted to discuss with you today, because as in the brain, as I anticipated yesterday, in the signaling mechanisms that animals use in order to communicate and actually deliberate, there are negative signaling mechanisms. So like in the brain, excitatory, inhibitory neurons and synapses, blah, blah. Here you will have same type of phenomenology. That's what the experimentalists tell us. So, before that, sorry, just wanted to comment that maybe, two sides is very simple problem. Yes, it is very simple. You can understand it very well. But promise, you can generalize that to many more options. And in the end, it will take more time. The numbers that are committed to the different options are going to be different. But if you study consensus, the way I introduced yesterday by comparing relative fractions, you will see that the problem and the values even of the consensus is not very much dependent on the possibilities that you have. This is something that you can see in some of our papers. We have studied that, so you can believe it. This is something. Then the criticality of the brain. Actually, this is my message that I already gave you. There is this criticality that it is connecting these two systems again. You are going to have lectures on the criticality of the brain. So I'm not an expert, but much better to wait till maybe this week or next week when people are starting to talk about that. I heard his talk of Christian Meiser, so he's going to talk about that, sure. You will see that there is this analogy there, sorry. And now I come to what I wanted to tell you. So there is this group in the UCSD, University of California, San Diego, led by Ni, I think that's the pronunciation, in which he, like the other one that I was mentioning yesterday, they have spent their lives studying the bees. And they have also recognized that apart from the waggle dance to communicate the possibilities and try to get a quorum, voting for the same spots, they also use, maybe it's not fun, not working. So here we cannot hear the noise. But apart from the one that is not very nice, but there is this that it is doing the waggle dance, and there are others there that also have options, and that they are kicking with their heads to the one that it is advertised in an option, and they actually make a noise. So there are people out there that have been studying that, systematically, and not for a period of time of 3 months, for years. So I kind of tend to believe it. So there are these negative signals that they use in order to, hey, stop dancing for that side. It's not good. Stop dancing. And remember, when they do that, they will do it through the uncommitted state. They will never do direct transitions in between the different states. Okay, this is something that it is peculiar from these bees. And one thing that I saw mentioned in one of his papers is that this signal that it is negative and allows them to stop recruiting more options, scouting for more options, is something that will be effective the moment in which the signal, the negative signal, achieves some sort of value, a threshold, let's say. So it's not immediate, not just one kick coming from another committed B that it is telling me stop. It's not enough. But once they have reached several of those bumps that are telling them to stop, they will start stopping. Particularly what I read in their papers, is that the scouting process actually is going down. So they don't keep on traveling to find more options, which is very nice because this is what we want, that the mechanism in the system that drives our pi parameter, which is the self-discovery parameter towards zero, right? And with that, in an adaptive way, and very nicely just using these stop signals, you will drive your system towards the critical point that was interesting to us. Well, not the critical point, the critical region, where this pi is 0, and actually I can see this contact process and the spontaneous breaking of the symmetry. Because, by the way, for finite system sizes, the fact that the fluctuations are breaking the symmetry for you is something that it is not very much happening close to the critical point. It is happening also for lambda values that are kind of separated from the critical point, which is nice. It's a finite size effect, it's true, but finite size effects are there in nature all the time. Because it will happen even if you have, like 1,000 Bs, 100,000 Bs. It will just take longer time for the fluctuations to reach that state that it is completely breaking the symmetry in between the options. Very nice. So this is what I am saying you here in this slide. It is true that these negative signaling mechanisms have been already taken into account in the literature in previous works related to this Bs modeling, opinion dynamics modeling. But the way they did it, which is very interesting, it was a bit more complicated, was just at the level of the deterministic equations without worrying about fluctuations. Again, keep on deterministic treatment. So the stop signals were introduced as what we call a cross-inhibition term in the equations, which are deterministic, and that will be similar to the ones that Ulrike is using to model population dynamics or to model the activity of the brain. Okay? So this is the type of term that you will have to introduce if you want to interpret that this cross-inhibition that happens there, instead of taking your parameter pi going to 0, is just introducing some cross-inhibition in the dynamic equation, in the equations of motion at the deterministic level. You understand the meaning of that? So the meaning is that if I am actually of alpha type, but I have friends around that are of other types, I am going to sum all the ones that are of other types, and the action of those that are of the other type are going to actually decrease my probability of having alpha type. Okay, so it is a direct reaction, let's say, or interaction in between alpha and beta, but that's not allowing them to, pass directly from beta to alpha. Forget about that. This is not going to happen. So those ones that are of beta type that are going to cross-inhibit the possibility of having more alpha type are just going to drop them down to the uncommitted state. Okay? See? So this is respected in this type of models. What is nice about that is that this mechanism also is automatically breaking the symmetry for you. But you will need to add this extra parameter that characterizes the strength of these cross-inhibition interactions. So there will be this parameter gamma that you will have to tune in order to break this symmetry in the deterministic sense. Then, by the end of the lecture, you will choose which one you like better, because all these interpretations are possible, and actually, when facing a problem that it is difficult because it's deciding in between two options that are identical, whatever of these mechanisms actually will be able to do the job for you. Okay? So that's another option. And in here, you will see that the system will pass from this fixed point in which nothing, not commitment, and no consensus, to a place in which there is commitment. And it will be a continuous phase transition, and is controlled by the pi parameter and the gamma parameter now in general. And this is all the work that we are doing lately. I mean, this has been done already in the literature, but we are revising everything carefully and trying to understand better what was done, and also to introduce the effect of the pi parameter. So you see here, this is the phase diagram. So here is the consensus phase, and here is the no consensus phase, and this is the effect that the parameter pi will introduce. So whenever pi is 0, actually you will always have the best consensus, even in this scenario. And if it's different from 0, you shift a little bit, no? In the phase diagram, the possibilities, no, of having consensus are a little bit reduced, let's say, okay? And these are the stationary values in order for me to show you that the transition continues being, in this case, continuous. Okay, it's a continuous critical phase transition. We haven't actually spent any time, and nobody in the literature, trying to characterize very much the exponents, putting these models either in lattices or in networks. You can do that, of course. I mean, you can put these models in networks that are static, dynamic, in lattices of all kinds, and try to study in deep this phase transition to try to see what is the universality class like. In this particular context and scenario, I don't think anybody has done that, but it's maybe an interesting thing also to do. And again, what I was saying is that pi equal to 0 still, is guaranteeing the best of the possible scenarios for you to form consensus. What else? Okay, we read about these papers about the negative signaling thing, and we saw, as I told you, that it is not that right away, the moment in which you have a little bit of other options there present in the game, that you start having this effect, immediate effect, linear effect, let's say, in the equations. So what we were seeing is that everybody was mentioning that was needed to have some sort of quorum, some sort of, accumulation of signals. So we just wanted to see what was the effect of instead having linear cross inhibition. That's the way we refer to it. We were putting there some complex contagion type of characteristics, which means that you don't do anything until the amount of signaling that comes from others that are competitors is above some given threshold. Okay, that's look a little bit more reasonable in order to compare with experimental data. So we did that, and we were replacing the cross inhibition that you saw in the last picture by a cross inhibition now is that it is complex. Why? Because here we are introducing these threshold models, these functions that are non-linear. And maybe you are going to think, okay, now you have too many parameters, too many choices, so things are going to be very much dependent on the choice of the nonlinear function that you introduce, and so on and so forth. No. So we studied that. We didn't study all the functions, but we studied these functions that are usually introduced in the context of also of neural networks, also in robotics, in general, these nonlinear functions to introduce thresholds and know how high you go are not common in that literature. And the idea is that you don't see much dependence. I mean, you see an effect, that's the positive message, but you don't see very much dependence. Important things don't depend very much on the choice, of the particular choice that you make. So the idea is that you introduce a threshold. Beyond this threshold, things are going to happen. Below that threshold, is not going to happen. The way then that you go, once you have passed the threshold, is not that relevant here. So this is represented in these 3 plots that you see here. Here I'm just telling you what is the value for the high quality of the bits that are voting for the high quality option. And for the different trials that you see here, they are very similar. Here there are some more discrepancies. This is representing, because this is, again, an stochastic dynamics, and it's not always true that you choose the best. You always make mistakes again. So you have a probability of making mistakes. And this is just quantifying how often you choose the right option in the implementation of the dynamics of this model. And actually, in this case, the nonlinear is worse, is giving worse results. Why? Because even if by one fluctuation you decide to kill the good option, it will do it more dramatically than the linear one. So it's reducing the good option, and then you have higher chances of making an error. Okay, so there are errors in here. But the time that it takes to reach the steady state and other observables are much improved if you have this nonlinear type of behavior in your system. So since we had different observables, we decided to define what we call a performance type of parameter, that it is comparing the positive cues and the negative cues all together. And with that, which is a little bit ad hoc, yeah, it's true, but it makes some sense. The idea is that we ended up, convinced that having nonlinear cross-inhibition, if you were to put it, is much better than just having it linear, no? Which also is in agreement with the current tendency also in the community of complex contagion processes. That, I mean, the assumption of things that are new in technology, in ideas, is not happening linearly and smoothly, but actually requires that you have maybe some nonlinear function, some threshold values that you have to. So if you see that everybody around you is buying, I don't know, that's for women more, or for men in general, in fashion, that is buying something that it is cool, maybe you don't buy it immediately when you see something around you, only one or two, but you need to see it many times, and then you feel more curious about it, and then maybe you eventually buy it, no? This is the example that comes to my mind because it happens for so many young people around. I mean, my daughter is always interested in what all the others are doing. I'm not doing that so much, but I mean, this in social systems is very much the trend, right? That you wait until you have enough influence from others in order to do something. So the bees actually doing that will perform better, okay? Good. So, and with that I finish. This is also research that is ongoing. And maybe you have heard about these higher order interactions, simplicial complexes, things like that. So the idea here is that so far, when we were building these deterministic models, essentially we are taking into account the possibility of forming pairs of different type, and committed, no? And this is not giving you the terms that in the deterministic equations are proportional to N0, N1, N0, N2, quadratic terms, because it's the number of pairs that you will have in a system that it is fully connected. In here, I mean, what we are exploring is the possibility of, again, is this idea of the complex contagion, that you need to have more quorum in order for you actually to be recruited, to imitate others, that you imitate only when you are part of a group, and in your group, which may be a triplet or 4 people or whatever. This is a generalization that you can do. They are of this, the majority, let's say, are of that particular type. And only in that case, this group interaction is allowing you to actually become convinced that you need to change your state. Do you get more or less the idea? This is something that it is very, in which the activity has been grown in the last years. And I think it's also natural. I think it's okay, it's fine. It's realistic. It's something that really happens in social phenomena, such as in decision-making, right? So this is a paper that was also part of the recommended literature that I proposed to read, because it's very nice. I think it's very clearly written. It's about complex networks, again, but to make it more simple, they also propose the mean field approximation, which is what we already know how to do, but now including what we call higher order interactions. The first thing that they did here, as we are also going to do now for the bees, this is for epidemic spreading, okay? So just one epidemics, one virus that it is propagating, for instance, and there is no competition in between two options. In here, there is no such a thing. But then you can write the deterministic equations that are the contact process-like type of equations that we have seen a moment ago, because there is only one type, so it's just the equation for the row. And then add these higher order interactions, and the higher order interactions that they included in this paper at the level of the mean field is just 3-body interactions. How will you model 3-body interactions in this differential equation? It will be, for instance, susceptible, say not infected, times the quantity of infected square, for instance. So it's 3-body interactions, so 3 multiplications of the density, in this case, of individuals that are in contact. See, at the deterministic level, 3-body interactions. So in this case, you will have rho 0, for instance, times, or F0 times F1, whatever, to power square instead of just the linear power that we were seeing yesterday in the hands-on session. Do you think that that matters? Matters, very much. Well, matters very much. It depends on what you search, But the idea, for instance, in this phase diagram that you see here, this is not my work. This is the work extracted from this paper by Jacopini and collaborators. is that you can have the following now, phase diagram. Here is the phase diagram. Well, this is actually the density of nodes that are infected in this paper. So this is the continuous transition that we have seen also, a moment ago. This is the parameter that actually is, because, I'm sorry, I forgot to mention, that it is not that you are deleting here the pair interactions. So I can get convinced because I have friends with whom I meet, I can get sick because I have friends with whom I meet, on a pair basis, like we have this chat together, the two of us. But I can also get infected by this group, three-body interactions, for instance. And I'm not deleting the other ones. So I keep the previous ones, but I am adding now the possibility of getting infected through group interactions that are not the formation of these triangles, the squares, whatever you want. Here is going to be triangles. If I add that, I have another parameter, which is the bad thing. So you will have one parameter characterizing the imitation as in the previous model. But now you will have another one that it is going to tell you what is the strength of these new interactions that are group-like. Okay? You can now, all of you, do that. It's simple. So the idea is that this parameter here in this picture is going to be this lambda delta, which characterizes these transitions in group. Now this group interaction, sorry. And here, lambda is like our lambda, is the same lambda parameter that we had in our model. And this is the new parameter that has now different particular values, given values. So for low values below 1, which is the point where we have found that we have the continuous phase transition also in the models of the bees, you will just increase a little bit the number of voters, in this case of infected people, but the transition will remain continuous. So it's a critical phase transition. Whereas, if this parameter actually is in this other side, bigger than 1, it's not just that you increase the number of infected, which is something that you expect, of course, but that the transition now becomes first order, explosive if you want. It's first order, you jump, and you have stability. So there is a coexistence in between healthy and infected individuals in the population. Okay? And this is what you see over here. Maybe you don't appreciate from very far, but this is discontinuous, and it's connected to what also Ulrike was mentioning us in some particular cases. Okay? Very nice, right? So, of course, we wanted also to see what happens if we introduce this, because we believe that they are there. The bees also need some quorums in order to be recruited and also to cross-inhibit themselves, both things. So the idea is to put that also in the model, the LES model that you all are familiar now with. And we did that, and you see here, I am telling you that I had added this new term now that is described by this parameter lambda2 that has into account the interaction of the uncommitted with the committed for whatever the options, but now to the power 2. So these are three-body interactions, as if they were forming triangles. So imagine in my robots, it's very easy, right? If my robots, if within my radius of interaction, I had 2 more robots with whom I am interacting simultaneously, then if they are of the same type, then I decide maybe to copy them with a probability. If I only have one, one now and one at another time, but they are not the 2 of them simultaneously there, when I am making the proposal of changing my state, I won't have that type of group interaction. So it's something on top of, And the idea is that, of course, for pi equals 0, which is what happens in these epidemics models, you more or less get back this line that I was showing you before in the phase diagram, that it is separating the consensus and the non-consensus part. The transition is here, with a dash and dotted line. And you see that this means that it is discontinuous, as it happens also there when the parameter that it is characterized in the higher order interactions is bigger than 1. Whereas, if it's lower, this is not valid. The fact that it is in gray here is that it is not a stable solution. Forget about that solution. In here, you will only have the possibility of maybe whatever you had in the original model without the higher order interactions. And the fact that you introduce the pi factor that was not there in the model of the epidemics is changing the nature of the transition from discontinuous, which is what you will have with higher order interactions, two continuous again, but that is not always the case. So there is a tri-critical point that actually is changing its position in the phase diagram with the amount of pi that you have in your system. Remember, pi is the introduction of information, fresh, new, into the system every time. Nice, right? So you have here a lot of possibilities. But that's just the density. No, here, as something that it is not happening at the level of the epidemic spreading, that I was commenting before, we have two observables. So on one hand, we will have the possibility of having no commitment, uncommitted individuals, as it happens also for the epidemic model. But at the same time here, we are breaking the symmetry again of the options. So when we have the phase transition, it's not only that the agents become committed and you have no activity in the system. No, here also we break and we have a finite value for M. So either continuous or discontinuously, you pass from not having consensus to having consensus. And you can, with these other higher order interactions, you can improve the area, the region in which the consensus actually is possible. And explosive, maybe you can even pass from having zero to having something that it is very big, not in a continuous manner as we were seeing yesterday. Get more or less the idea? Nice, no? Okay, so this is what we have here. And I just wanted to maybe, digest this information that appears in the phase diagram a little bit for you. So just consider now the situation in which we forget about the pairwise interactions, which are not enough. Now we believe that maybe pairwise interactions are not enough, that I need to have at least a quorum of people interacting with me and in these triangular groups, having majorities for one of the options in order for me to get convinced. So if just forget about that, just to simplify a little bit the picture, this is what you will see. You will have a coexistence for pi equals 0 in between the uncommitted, so everybody not decided, and the committed agents for one of the options, because this is the behavior of rho, and exactly this is the same behavior for M. So if you have that M is equal to plus minus rho, it's only possible that all the B's unanimously go and vote for the same option. It can be any of the two, so that's why it can be positive or negative. But there are no other B's that are maybe competing with them. So the moment that that happens, actually you break the symmetry totally in favor of one of the options, which is very nice. It's something that I was not expecting to see. And then increasing the value of pi, actually you eliminate this biastability gradually, and actually you can even become, so here I'm just showing you the flow diagrams that you will see in this dynamical system. And eventually with pi, actually you can control whether the transition is going to be either continuous or discontinuous. Eventually, the two solutions that here were separated. The stable ones are, depicted as solid lines, and the broken lines are just unstable. Here, you become joined now together that way in a continuous manner. And this is something that you can actually tune with this discovery parameter. Whether that is going to be relevant for the bees, I don't know, maybe, no. But it is true that you can play around with all these parameters and phenomenology in your swarms, artificial swarms, if you want to deploy these models into robots. Okay? Depending on what is your interest, you can always play around with these ideas. Okay? That will be the final message. And I also wanted to see whether beyond the deterministic treatment, the fluctuations here are going to play a relevant role, as they were playing an important, very important role in the case in which the model was the initial model, very simple. Here, once you have introduced these non-linearities, this possibility of having higher order interactions and so on and so forth, the fluctuations are there. So the deterministic average solution is still good, but they are not destroying anything. They are respecting what you have, and you just have a probability of having values of F or of the consensus around the average value that you will get from the deterministic analysis. Okay? So they are not destroying or changing the physics or the phenomenology in here. Okay? Well, so far so good, because we haven't explored everything. So this is work that it is ongoing. So excuse me, maybe I'm saying something now that it is completely, not completely true. And this is just the same. I'm just showing you that the transition is passed from being continuous to being discontinuous with the increase of these higher order interactions beyond the limit, which is equal to 1. And eventually, how the pi is again restoring the continuity. But the fact that you have this pi, again, the message is that it is reducing very much the region of the phase space in which you will have consensus. So the best always will be to have pi tuned down towards 0, okay, which is what apparently these stop signals in honeybees is actually producing, okay? So with that, I think that I am now finished with this part. I hope that you like it. I'm just going to present you some summarizing conclusions in here. So the idea is that many animals out there, not only the bees, rely in pulling information independently from their environment and then socially sharing that information with other bees or other animals. And this is the basic ingredients that we have included in this model, together with the fact that they are able to assess the quality of the options. So these are very basic ingredients that are good for the bees, but maybe could be good for modeling many other systems. This is something that you might have in mind. And with those constraints and for all the possibilities that we have been describing in the previous pages, the conclusion is that the bees are able to really find strong consensus for one option, sometimes even in difficult situations in which the possibilities maybe are equal and it is difficult for them to decide. And we have discussed and seen the different mechanisms that are there and you can use in order to break the symmetries in the case that you have those symmetries. More or less, this is what I wanted to tell you, and you can read them here, but that's the message. And maybe you can use this model for your future research endeavors, and I will be happy, if that's the case, because I will feel that, you have learned something in this school, okay? So very good, and with that, this part is finished, and this is the suggested reading that I have summarized for you. There are so many papers out there that I will be just presenting you 20 transparencies with papers if you want to have a better knowledge of what's going on. But this is what I have used, and I hope that you find them interesting. And now, I just wanted to show you this movie because we are going now to study fish motion, but I'm not the sheep girl. I think this Fernando coming next week that it is going to talk to you about sheep behavior. But be aware when they describe to you the formation of these collective patterns of motion and so on and so forth, because most of the times the models that we present are like trying to be inspired only on the social interactions, alignment, no. But pay attention because in this beautiful movie here that I have also obtained from the YouTube, there are many other factors that are present. Maybe you pay attention, maybe you didn't. But in here, in order to pass from these formations that are sphere-like, there are dogs that are running around, and there is the guy in the middle. I have a friend that is a shepherd in my village, in my hometown, and actually they do, and the sheep are actually obeying them so much. So beware, because what I'm just trying to tell you is that it is not only social interactions that matter, but also the perception of the environment, the fact that there are different options, and in this case that there are some external elements there that are contributing to the formations that you see in the movie have to be taken into account in the model sometimes if you want to do real, or something that makes sense somehow. Okay, so this is something that you have to take into account because now we are going to go to the fish, and the fish, unfortunately, that I am studying, they have to make movement decisions. It's just a generalization of the problem of the bees, but it has to do with the direction of motion. And why do they do that? And why do they, the estorninos in the sky are changing directions? Sometimes we can believe that it is coming from, their internal activity. They are playing. I imagine them like children playing in the playground. But sometimes it's also that they are perceiving something that maybe we are not able to see. Now, in the fish that I'm going to describe in a moment, in the experiments that we have in Barcelona, they are within a tank. We cannot study them freely in the sea, unfortunately, because you will see that the tracking is the most difficult part in those experiments. And it's true that there the environment is boring. Yeah, yes, they are no in between four walls, but they have the walls. So they have to decide that the wall is coming, and I don't want to jump into the wall because I won't be very good for them, right? So maybe the wall effects are there, yeah, for the motion, yes. But it is also there for their decision process. Because when they see the wall, they will have to go somewhere else. They have to turn. And there are many possibilities open for them actually to turn. And many times, one is maybe not the one that has this information first and is going to affect the others, and so on and so forth. So you see, I didn't have still not the time of the hands, no, to maybe, because my goal, I tell you, is to try to, make a continuous path in between what I was telling you about the discrete decision problem and this continuous decision problem that maybe the fish in this fish tank has to do. So I would like to, join the type of modeling approaches, in going from the decision process that it is discrete to the one that it is continuous. I didn't have the time maybe and the students not to do that. But I think that it is not completely impossible. I think that there is some sort of transition that one can do. And not only for building the models, but also for obtaining results that resemble very much what you see in the experiments. I have this ambition, no? But now let's go. Sorry that I will take some time until I get out of here and go to the other presentation. It should be open and fast, but if you want to ask me questions, now is a good time. Yes.
You briefly talked of the decreasing value of phi of exploration rates. At a high level, it seems to be like an annealing optimization problem. Like you
decrease the temperature, yeah, the noise kind of, yes.
Does it increase consensus on the best option to do that?
Yeah. Yes. Yes. But you have to find, how, you can model it, and I did it already, I put you there an equation which will allow you to, anneal, go take this parameter down easily. But, you have to verify experimentally if that makes sense. You need some reason for that to be the case in animals, no? And I was providing you a reason for that to be the case, no? Which is this negative signaling that they use in order to reduce the number of scouts going out and trying to incorporate new information. Yeah, from the modeling point of view, we can do everything. It's true, but I think that we are physicists and we are more than mathematicians, and we need to really connect. This is, my way of working with the possibilities that the experimental work allows you to do, and whether it makes sense or not. No, it's also our responsibility to do that. Okay, but that's just what I'm just saying. Okay, so this is the other talk. I'm not sharing, eh? Okay, so I have to dejar de compartir maybe, and then compartir again. Yeah. Okay, so I forget about the first slides. That was supposed to be what I was going to maybe do today from the very beginning. I go a little bit faster. So you've seen already many examples in nature. I don't have to insist more on the idea in which animals behave like if they were one, as if they were a superorganism. Many entities, but behaving in a kind of very well coordinated way. And they have these formations or these patterns or these whatever. Dynamics have different names depending on whether you are working with fish or schools or flocks, if it's birds. But in the end, the idea is more or less the same. Individuals moving together as one. And here, what we are going to be interested in is in describing how this order, this consensus, is whether it's something really strong, rigid, if it's something that it is durable, if perturbations can easily break it, how do you control that at the level of the animals? These kinds of questions and many others. Questions are there, and there are many. So the idea is that we want to see how resilient is the order, what can you do in order to models that can allow you to have such things. And one thing that I want you to notice is that the order is not rigid. You have seen the animals moving around, and for the reason that it is, that can be different reasons, they change, no? The ordering, sometimes they exhibit intermittency in between ordered states and disordered states for a reason, or maybe just for the fun of it. Who knows, no? So we want to understand and better model, better and better, no, this type of behavior that has to do with living matter, active matter, out of equilibrium, and so on and so forth. Nevertheless, maybe not so many people have told you that there are also striking errors. The movie there is not very good, but the idea there is that this ship were in circles, no, going around for many hours, or maybe even days. I forgot about, I mean, I put that video at the time that appeared, no? And maybe Albert, who is the one that will send me, you know, Carmen, have you seen this? And this is an error. So they stay there without eating, without sleeping, because they stay, no, in that whirling, no, pattern for very long. And another one that you see here on the right-hand side, that this flock of birds actually jump into the floor because they make errors. I mean, it's living beings, right? I mean, it's not perfect. It's not even computers are perfect, but these are living beings, and they make these errors. So we want to understand, I mean, whether these failures also, no, can be there, no, in our models, and is realistic. By the way, this also has nice, apart from understanding the collective behavior of animals, this has also nice applications, not only, you know, in the swarming robots, that is true, but also in the graphic, no, the people that are doing, no, the graphic design, no, for movies, you know, animations and all of that, because nowadays it's becoming very, very realistic. And if you want to be very realistic, I mean, it's how this story started. No, this, you know that this big check model is Wanacam. But I mean, was inspired by the work of somebody that was working Reynolds, no, in the industry of the graphics, no, in the graphic development of graphics for animations, for movies, no, and things like that. You know that these days these people are doing physics in order to be realistic. No, I always put this example to my students in the physics of fluids class. Do you know the movie Avatar? The cascades, the beautiful, no, scenery that they saw there. They are using, no, the Navier-Stokes equation and the numerical solutions of the Navier-Stokes equation, plus optics, plus many other things, in order to, no, provide, no, those graphics that look so real, no, and they are always generated with computers. I say that not just because you need, no, to know it. It's because maybe for some of you, in the end, you are going to find jobs doing that, doing physics for, you know, the film industry, or who knows, no? Who knows? You will have to tell us. But I mean, some of our students in physics in Barcelona have found jobs that have to do with that, no? With animation, with graphics. And this is the movie about the zombies, no? Anyway, just for your fun and entertainment. This is the outline of what is coming in the next days. Collective motion and collective decision-making, because they are related. Now, in grouping animals, first of all, I'm going to motivate this part with real experiments that we do in Barcelona. And then we are going to start by proposing what we call, no, what you call, what everybody call, data-driven models. Well, I'm not very fan of it. I mean, I do it because, I mean, it's the trend. Sometimes you have to do what also the people are doing. But it is true that in there, the pros is that you can be very realistic and nice. The cons is that usually you have too many parameters. I don't like that very much. But that's the pay to price. No, that's the price to pay. Then I am going to tell you a little bit about this actual model that we propose, that it is something that we call selective interactions. This idea that not, I mean, in these models you have reciprocity, which is also something that it is very natural in living systems, right? I may copy, very successful scientists, but maybe not so much, what unsuccessful from the point of view of the publications and things like that are doing, for instance, doing research. This selectivity is very much also operative at the level of animals. So they have preferences like us. Maybe not so sophisticated, but they have preferences. And we are going to use that, by the way, is also called in the literature these days non-reciprocal interactions, not that they don't obey the third law of the Newton's law, the third Newton's law, sorry, and it's very much out there. So we didn't call them non-reciprocal because, I mean, I don't know exactly what that means here in the context of social animals, but selective, yes, that they pay attention which is selective to things, is important. What else then? I will also discuss with you signatures of criticality in this superorganism that it is going to be this fish school that we have characterized both at the level of experiments and also with some models that we have proposed. Not completely, totally satisfied with them, so still a lot of room for improving. And well, let's see, maybe if I have more time, I have more things that I could include, but so far I think that that's a reasonable program for what is coming. Okay, so I present you our fish. This is the species that we have in Barcelona. We have 100 of them in a small room. No, it's not in my office, don't worry. It's somewhere that the University of Barcelona allows us to put animals because it's very demanding. So you have to hire somebody that is able to manipulate them and also with the given training and permissions, let's say. So that's just already a difficulty. And this is a real image. I mean, it's not something that I got from the internet, but it's a picture because we were publishing a paper in PNAS and we got the cover. This is something really nice, that you get the cover of the PNAS. I'm going to come. Yeah, I'm going to explain to you all the details. Don't worry. No, it's not very big, but it's big enough. Okay, so this is the species that we are going to study. They are called black neon tetra. They have this horrible name that classifies them, but so here is passing, but the screen is blocked. So in my computer, I am passing the slides, but here I am not seeing them. What do I do? Get out and get in again? Oh, no. Okay, so now I have passed maybe too many. Sorry, now it's too many. Okay, now I got it. Okay, so sorry. Yeah. Okay, so this is the tank. This is the fish. This is a recording, a normal recording. But we have superposed on the recording the tracking already. So the most difficult part of this project that we started already in the pandemic times, when we were not able to go to the lab. We started at that time, so in the beginning we had to work with data that was already there, not very good. But now we are able to do our own experiments and recordings and repeat many things and change things. So this is the type of effort that you have to do to track the motion of this fish. What the tank is like. The tank is a square meter tank. It's a square in this case. We didn't actually round it up because well, there is apparently no reason to do that, but I mean, if you want, we could also change the shape of the tank. We cannot really go to much bigger sizes, unfortunately, because the room that we have in this infrastructure is small, so it will be horrible to be there doing the experiments. And we have up to here, we have tracked up to 50 fish, which is not very much, I know. We have 100, but the tracking techniques and technologies these days don't allow you to track many more, especially if you are, demanding. So if you don't do a lot of mistakes. Why? Because this tank is actually with 5 centimeters height of water, which is shallow enough in order for them to be almost moving in quasi 2 dimensions. But still, if you have many of them, you will have what we call occlusions. So they pass one on top of each other, and resolving those occlusions with the tracking technologies that I'm going to describe in a moment still is a mess. So you have to solve so many errors by hand. And we don't want to do that by hand because it's forever. Yes? No, because they were there. We met these psychologists that are there in the University of Barcelona that themselves started doing these experiments, and we knew about them through a student that then did the PhD with us. And she was doing the master thesis with them, so we knew that they had that, and we continue with what they had. We could change, but not everything. I mean, it's very rigid. So we also have these, how do you call them? The ones that are used also for the embryo. Zebrafish, we also have those. Not that many, but so far we have continued with those ones because they school, whereas the zebrafish, they don't school. They just, what they do is shoal. So they aggregate, but they don't orient themselves in in this way so nicely as the ones that you are seeing here. So they are not polarized. No, the zebrafish are not polarized. If you imagine them like if they were vectors, they won't actually orient themselves along the same direction. And they are more agitated, no, in general. What we have in mind is also to make an experiment in which we mix them. I don't know, just for the fun of it. Yes? Like that? I mean, you can stay there. Well, first of all, they sleep. I mean, it's not that they keep on moving the whole life. No, so we put them here when we want to do experiments during the night and when we are not working with them. Actually, they stay in their houses in less numbers. So maybe in every house we have 20, and we have several houses. And they are fed there. They have treatment. So there's a lot of things that you have to do. Otherwise, in 1 week, they will be dead. And if you treat them well, they can live for years. So we have even no reproduction events within the homes of these fish. So we have little ones that are being born, but we don't use them for the experiments. And it is true that it is important for their activity that you have not them. They are in the houses. We transfer them smoothly. First, they go to a place where they stay some time because you are removing them from the natural habitat with some, I don't know how to call that in English, some kind of net. So you put them first in an intermediate compartment, and then eventually with that compartment, we put them smoothly into the big tank. And everybody knows that there is a little bit of stress going on in moving and manipulating them. But it is part of the game. So fish also in the ocean, in the natural habitat, they move because they want to find food, and also because they are stressed by many different reasons. So if you do the experiment, for instance, for more than 2 hours, you will see that the activity goes down because they are not fed in the big tank. So they just move around, trying to explore. We have even experiments in which we see the difference in behavior when they are more habituated and less habituated, and we mix them. This is something that I'm not going to describe here because it's very far away from the topic of the conference, but we do different things with these fish. And it's true that the transfer is like that and provides some stress to the animals, and that stress is what is probably responsible for the motion that you see in the swimming pool. Still, the motion could be of different kind, and this is what we see, okay? This cooling behavior, reaching the walls, turning, and deciding where to go. Who is actually leading that, if any? How do they decide? This is the type of questions that maybe one can ask in this simple setup. We have other setups, as I told you, and if you want to know more, you come and talk to me. Yes. Sorry. Because we are physicists. We are physicists. Are you a biologist? Okay, biologists start like that. I don't want to criticize that because it's the way also that science advances. But it is true that if in the first model, without understanding anything, because it's not true that we understand, we still don't understand many things. So if in the model that you start with, you start putting all the differences and specific things of the different species, you are not going to understand anything. You are going to get stuck. And we don't want that, because we are physicists and we are studying this problem with the eyes of physicists. That actually maybe is in contradiction a little bit with the specificity that biologists will defend. I don't mind doing that because it's good that we start from the different approaches and maybe eventually we will join somewhere. But it is true that physics, imagine if you have argon and neon, I don't know, they are very similar maybe. I don't know if it's a better example. No, but when they were studying the noble gases, don't you think that they had the same doubt that they were very different? And eventually you found the equation of states for the ideal gas, and it's good for both of them. See? So if you start looking at the problem with eyes that, tend to see the differences, I think that you are never going to find what actually makes them more similar than you believe. So this is a problem, I think, in biology. Because it's true that you are caring very much about something that it is of detail, you have to do a specific modeling. But if you are interested in understanding the collective motion and decision-making and so on and so forth, maybe if I was able, it is very good to have experiments with fish and with sheep and with ants, no, and everything in order to actually explore whether there are some commonalities in between all of them. And biologists sometimes have the resilience to believe that, which is good and not totally good, in my opinion. For some things it's good, for some others no, because then they don't have laws, they don't advance. No? So they spend their lives studying just one species. Okay, good, but no, I mean, I'm a physicist, I'm not worried about that. Do you get more or less the idea? Yes. Any other question? Anyway, okay, so let's proceed. No, I was telling you that the most difficult part of this project actually is the part that the students and the technicians that we have hired are doing there. It's very hard because you have to use this ID tracker, which is the one that we chose. Maybe you know it. It's an algorithm that is open for all of you actually to go and download and use. But you need to have computers that are very powerful because it will operate on the graphic units of your computer. And also is used in machine learning. Every time more and more machine learning is also introduced into this field of movement and behavior of animals. So the idea is that this code, you don't understand very well what's going on, but the idea is that it is using some pieces of the videos that we feed there in order to try to kind of recognize the identities of the fish. Why? Because when that happens, that you have these overlaps, they can use that in order to distinguish which was first and who is coming after the collision or this superposition of the fish. Because many tracking algorithms that you will see there that are much easier to use than this one will make lots of mistakes. And depending on the question that you are asking, maybe that doesn't matter. If you are interested in density, for instance, distributed in space, who cares about the identity of fish? But if you want to calculate velocities, accelerations, which is something that I am going to do, I want to make sure that my fish is the same fish before the collision than after the collision, you see? So this is very important. And if you make mistakes, I don't know what you are doing, so you have to be a little bit demanding. And we have to resolve manually some of these occlusions. It's unavoidable. But with some of these tracking techniques, less and less, more automatically and more automatically every time. Actually, one of the students that appears here, the first one, started with us doing a master thesis after he finished the master, and now he's hired by this ID tracker people because he was doing so many improvements to the software that we started using that they hired him to do that better for everybody. So now the new releases of this ID tracker that you can find on the web freely are much better than the ones that we started working with, just because of a physicist actually improving a lot what was going on inside there. So I wanted to mention that because I want to thank them, because without them, I mean, this project is impossible. You need here a lot of people working. Okay, this is for the occlusions. And this is the type of observables that actually we will be paying attention to. In particular, we will have positions, trajectories, and from the trajectories, we will calculate velocities and accelerations. If you are interested in the technical details, come to talk to me. But the idea is that with that, we are going to try to build coarse-grained descriptions, models of different kinds, models that are usually inspired by this experimental data and observations that we have in our lab. And I wanted to start telling you that this is the type of average speed, the modulus of the velocity that you will see for the center of mass, let's say, as an average for the group. This is how the velocities look like as a function of time. So in the big check model that maybe some of you know, the assumption is that the velocity is constant, right? And that the particles only reorient themselves randomly and by aligning with neighbors. Here you start seeing that the velocity of many fish species is not constant. It's something that looks like periodic, quasi-periodic. I mean, maybe not just one frequency in here, but it's something like that. And this is known. This is what it is called the burst and coast type of dynamics. So fish actually move the fin, their caudal fin, in order to propel themselves, and then they let themselves go. So it's not that they are constantly doing that. They do that, advance, accelerate, and then they let themselves go, no, just no, as when you swim, so you advance again. So they do that all the time. So, well, this is nice. We see that, Bastan Coast. Oh, sorry. Look at the nice movie, because now that I put it. So this is representing this Bastan Coast. By the way, from the point of view of hydrodynamics, this is wonderful, because you know that when we have a boat on the water and also a fish on the water, the motion that allows you to propel is also generating these vortexes in the liquid. And it's not completely relevant for what's actually going to be the communication that you have in there, in between them. Because now we're faced, I was asking Ulrike this morning, what is the connection in between these entities if you are describing animal motion? It has to do with lots of inputs, has to do with sensory, information that comes through the eyes, maybe in some cases with the ears, such as in the sheep. And here, for instance, the hydrodynamics is going to play a role. And not only the hydrodynamics, it's also that they are actually, the fish are known because they have an organ, that it is the lateral line is called, that it is actually able to sense pressure changes in the water in which actually they move. And all of those actually are coexisting and maybe are relevant for the type of information processing and the communication that they undergo. Okay, so first of all, I want to understand. So first of all, shall we start always with a group? Maybe yes, maybe not. Let's try to understand what happens when we increase the numbers from 1 up to the 50 or 40 that I was showing to you. So this is just a little fish there. I don't know if you see it. It's a little one there, and it has the same dynamics, although there is a little bit of adaptation in the Barcelona coast when there are many. So they adapt a little bit to living in groups. Whereas in here, he's alone. There are 3 replicas there. So these 3 different trials that we did with independent fish. The first thing that you notice is that it is very much scared. So it will have a tendency very much to go to the wall. But after a while, he will be able to do, separations from the wall and go into the middle, not much. But the moment in which you put 2, 3 more not together, they will be braver, and then they will explore the space that they have available much better than when they are alone. And I wanted to show you that this is the type of velocity as a function of time. This is the speed, so the modulus of the velocity as a function of time. And you see this kind of periodic, quasi-periodic, well, whatever, wavy patterns that you see at the level of the individual fish. This is the distribution of these values of the speed, and it's bell-shaped, nothing very interesting. And this is also what we call the turning rate, that you could measure in different ways, in particular using this formula, but also just by looking at the differences in the orientation of the velocity in between snapshots. So this definition actually allows you to capture the same physics, but without depending so much in the resolution of your movie. I didn't mention, but the movies are captured now with high resolution. So it's 50 frames per second, and I saw you before the pixels, but it is 5K, so it's high resolution. And we record, by the way, several realizations, several experiments with different numbers, and for durations that go from half an hour to 1 hour. After 1 hour of the same experiment, we see differences. It's like they get tired. I don't think that they have the same dynamics. And it's something that nobody tells you, but it's also something that happens in non-animals. They don't move constantly in the same way as the function of time. No, it's impossible. They need to eat. They need some motivation for that, to be the normal state. And if they lose the motivation, they won't continue moving in the same way. So there is some temporal drift and effects in these observations. And you have to say it, because it's the real thing. Okay? So one fish, now I put 2 fish together. It doesn't matter whether you put them very far away from the very beginning or close. They will see each other, and immediately it's like if they, but very far away, it's 1 meter. And they are, by the way, I didn't mention, they are 2 centimeters long, so there is plenty of space. So they could be independent and live in half and half of the space for each one, but they don't do that. They like to stay together. It's a social species. And the moment they glue together, they'll stay together forever. And this is the type of speed that they will have in these experiments in which, and this is also something that you can do. The probability of having one in the center, that the other one is around you in the different directions and distances, and higher, so darker colors actually are representing higher probability. So this is the region around the focal fish that it is in the center that they will very much like to be. And apparently, they don't have so much preference for any particular orientation. And that's because what I'm going to show you next is that they start chasing each other. So it's not that one is always the first and the other one is just following. No, they constantly exchange positions. Again, the idea of the children running in the park is very good for describing what fish are doing. So nobody wants to be the last. One runs, the other one runs faster in order to catch it and not to lose track of what the other one is doing. Like that, competing, kind of competing all the time. It's very interesting because it's something that you need to know also when you propose models. And here, I'm going to show you one way in which you can calculate whether one fish is effectively a leader or a follower. Imagine that in these two fish, I will have one that it is more dominant, that runs faster, that it is stronger or something like that. With this type of temporal correlations, you will be able to see that, it's a leader is always going in front and the other one is going to be behind. What we measure in here, this is a system of reference that actually always moves with the fish. And you see that they exchange and rotate around themselves all the time. So it's not this big sick idea of fish moving always, like if they were spins in a lattice. No. So they constantly, reshuffle their positions. And this is something that happens here at the level of two, but also it happens at the level of many, constantly, trying to organize themselves around the center of mass or wherever the neighbors are. And as I was saying, this is trivial, but let me explain it to you, what is measured in these correlations. These are temporal correlations in the velocity. You can do it with the modulus, or you can do it with the orientation. I think that in here is just the orientation, but you can do it with both. And the idea is that if I am a leader, you will copy me at later times. So the higher value of the correlations actually will come at later times. So tau being here positive means that somebody is highly correlated with my orientation, but at later times, T being positive. Okay, so that means that I am the leader and you are the follower because you are going to adopt my orientation at later times. If that was the case, always, that you are a leader and the other one is the follower, the tau will be always positive. But here what we are seeing is that the highest value of these correlations also sometimes happen with -2. What does it mean according to the measurement that we have over there? That the one that actually is copying is not copying, is copying in the past, which means that actually is a follower. So the higher value of the correlations occurring for negative values of tau means that the focal fish, that it is the one that I write first in the correlations, is actually a follower. Why? Because he is actually going to follow the one that it is J here, characterized as J, at later times. And according to this formula, tau has to be negative for that to happen, according to this formula. Get it? So this, just to illustrate to you that they exchange positions and this leadership. It's something that it is constantly being reshuffled, and this is something that happens at the level of two, but also happens all the time at the level of groups. Okay, very good. Now you have many of them. You calculate this average speed, and this is what I was showing to you in the first slide. Here are the different trajectories, the distributions of this velocity at the level of individuals and at the level of the average, different realizations in the group. The average behavior here, we are also showing the fluctuations, which means what is the individual velocity with respect to that average value. When I say velocity, excuse me, but I'm always usually here referring to the speed, so the modulus of the velocity. So you see these quasi-periodic oscillation patterns in which the first thing that maybe you notice is that it's not perfect, but it's some sort of synchronization going on, right? Why? Because otherwise you will have noise, or a signal that it is much more noisy than what I am showing to you here. So there is some sort of synchronization. The fish are synchronizing. Maybe they are even this excitable media that Ulrike is describing through these oscillators in the models. So the first thing actually that you could try to understand is why, this synchronization is taking place in the motion of these animals. What models you can use in order to describe that? I am proposing some homework. Well, first of all, let me just describe that also. The other observable that everybody looks very much, is this polarization that I was mentioning. It's like the magnetization. So you now sum the velocities in order to calculate with the vectorial character component, different components separated. It's a vectorial sum, let's say. If you have two vectors that are like this, you will get 0, right? So this is what the polarization is measuring. And here is normalized by the velocity of each individual, because we are here interested only on the orientation. We don't care about whether this velocity is higher, and that's also incrementing the polarization or smaller. So we want to normalize and just take care of the orientation. So this is the plot of the polarization of the group as a function of time, and maybe you can, if you want, superpose the average speed and the polarization. And if you are positive and you don't focus your attention only on the discrepancies, you see that there is some sort of correlation in the temporal dynamics of the two observables. And this is what we measure in here, the correlations through the Pearson coefficient of the two observables. And actually, this is done at the same instant of time, which is not the best, because there is this retardation effect that also Ulrike was mentioning this morning. So I see the others, and I want to orient like them. But this is happening after a while sometimes. And then the best correlation actually is never obtained when you calculate correlations at the same time, but when you calculate correlations with a little bit of lag, of a delay in time in between the speed and the response of the system in order to have these reorientations. But as I was saying, this is not the first evidence that you see, simple evidence that I wanted to show to you. What can we do? And this is my proposal if you want to work harder, this afternoon, maybe tomorrow, the day after, whenever you want at home, is that you propose a model in order to see if you are able to observe similar phenomenology in the model. Okay, so similar velocities and similar polarizations, and this synchronization, and see what you can do in order to, as a physicist, propose a model that is describing that with good accuracy. So the first thing that maybe comes to your mind, and that was my proposal because it's very easy, is to propose a kind of a Big Shake-like model. Who knows the Big Shake model? I thought that maybe everybody was familiar with the model. Not so many. Never heard of this model? Oh, okay. So do you know the XY model for magnetism in classical statistical physics? No? Oh, okay. So maybe it's not so easy. So the idea of this model, I'm describing it in here. Maybe that's the last thing. Sorry, 4 more minutes. And the idea is that this model is very simple. So every particle in the Big Shake model will be in a box with periodic boundary conditions, continuous positions, times. So just kind of Newtonian dynamics, but we drop the inertia. So it's just a force. So, sorry, if you have never seen that, maybe I need. So the idea is that these are particles that usually are moving in a media that it is offering them some also drag, some friction, some friction effects. So the idea is that if you wanted to write the Newton's like equation, you will have to write an equation for the velocity of each fish. Well, you can take into account the mass or forget about the mass, which is something that we usually do. And this is just the sum of forces, right, that are acting on fish I. What kind of forces do we have in here? You essentially have at least the following force. Imagine that you only have one fish. What kind of force I have to introduce in here? So first of all, you will have a force that has to do with what we call the drag in hydrodynamics. So the fact that the fish is maybe not moving with the velocity of the media is going to provide you, when if the media is at rest, it's going to provide you this drag. Here it will be the fluid velocity if you want, but maybe the fluid velocity is going to be 0, so forget about the fluid velocity, and just drag. The drag force will be something that it is proportional to the velocity that, and this is the drag coefficient that takes into account the viscosity of the air, of the fluid in which they move, whatever, okay? What else? Well, now, if the fish is not alone, you are going to have some interactions that have to do with what your neighbors are doing. Maybe hydrodynamics, maybe because you see them and you do something because you are a particle that is alive and can use energy in order to propel yourself and do things, okay? So physicists, in general, we write equations in which there are some relative forces in between the different fish that are out there, some interaction forces in between them. And this is nowhere the Big Shake model actually is contributing, simplifying this picture very much. And eventually, you will have some sort of what we call noise, this Langevin equation that I was talking to you about, some noise, because no, it's not a deterministic process, and you see that just by looking at the velocities of the particles. Okay, so what we do is to work in what we call the overdamp regime, in which this is neglected. So what we assume is that the velocity is going to relax immediately to some sort of equilibrium value. And we forget about the acceleration because it's happening, the variation is happening in temporal scales that are very fast. Because of, here you have at least this force that it is much important than what is on the other side of the equation. So eventually, what you will do is just write an equation. If you plug in this, you will be able to write an equation in terms of B, which is, by the way, the derivative of R with respect to time, equal to the other forces that are here. Okay, so nice. So this is what we call the overdamp limit, because we forget about inertia. This is the majority of the models that you will see out there in order to simulate the behavior of animals will be in this overdamped limit. And then you will have just velocity equal to these forces that it is just representing what I told you here, neglecting inertia, okay? So Big Shake went beyond that. And the idea is that, first of all, the forces that are going to be there are those, but he was not even considering the idea that the velocity was changing in modulus. So every entity there is going to move with the same constant velocity, and the only thing that matters is the orientation of the particle. The time also is going to be considered as a discrete variable, so it's proceeding in delta t's, units of delta t, and then you are going to update your position according to this equation, and the velocity is given by this expression there, and you are going to update your position according to the velocity that, by the way, has to do with the forces that you have on the second part of the equation. And then he assumes, as I was saying, that the velocity is just something that is changing the orientation, not the modulus. The modulus is going to be constant, equal for every particle, and the only thing that these particles are going to do is behave like if they were spins that are reorienting themselves by the interactions that you will have with neighbors. So this is the alignment rule, and it's synthesized with this figure here. So you consider that you are surrounded by neighbors within this distance, that it is an arbitrary parameter in the model. And with those that you have there, you are going to actually average their orientation, and you are going to align yourself with those. This is what the model is doing. And then you introduce the noise, and this is the equation for the evolution only of the angular orientation of the velocity, okay? So I was proposing that you do that, but that instead of just playing around with the usual and original model that Big Shake proposed, which is very simple, and that allows you to see discontinuous transition, for big enough system sizes. Now you incorporate some variability at the level of the speed modulus, okay? And if you do that, well, maybe tomorrow, if you have the time, or maybe by the end of the school, you can tell me what do you get. I know what is the answer because we did it. So the idea is that you may introduce in there some speed that it is changing as a function of time, like if it was an oscillator, for instance. And then maybe you can put them all the same and just simply play the game of the alignment with your neighbors and see what is the outcome, both at the level of the speed and also at the level of the polarization, and see if it's enough. Still, you haven't explained, why the fish are going to move in time with the same frequency and the same phase. So this is something more sophisticated that I'm going to discuss with you tomorrow, okay? So thank you for your patience, and we continue tomorrow, and maybe I'm going to show you some of the results that you can yourselves obtain in one afternoon. This is not difficult. You can start with 100 particles, with 20 particles, and you can start seeing things already. And if you need help, I'll be around. It's nice to have some model like that, around. It's good. Okay, so thank you very much, and I'm open also for more questions. Yes, we are late for lunch, sorry.
No, everybody's hungry.
They're hungry. Yeah, me too.
Okay, so I'll see you back here at 2:30. 2:30, yeah.